All right, welcome to the Real-Time Digital Signal Processing Lab course at the University of Texas at Austin. This is Lecture 4, Part 1 on sampling and aliasing. All right, so Part 2 is separately recorded. I've already recorded Part 2, oddly, this morning. So Part 1 is data conversion, sampling, and the effect in both the time and frequency domain and the sampling theorem. So a lot of this is going to be review of sampling. We've done it, used sampling quite a bit during the semester. We'll hopefully go a little deeper today. So in data conversion, sampling plays a major role in the analog to digital conversion process in our ADD converters. And we'll talk about the components here in Lecture 4 and later in Lecture 8 when we do quantization. So in the ADD converter, this is a theory of how it works. How we implement it is usually quite different from this. But the theory is we want to, in the middle of this, we're going to sample. And we're going to sample at some sampling rate, Fs. And we know that from the sampling theorem, what we can capture frequencies up to what by sampling at Fs? Half the sampling rate. So I can capture frequencies. So the sampling here captures frequencies from minus half the sampling rate to half the sampling rate. And this is going to give us a periodic spectrum after sampling. Now, one of these frequencies has to be included to make it periodic. So really, you have to include either half the sampling rate or minus half to make that periodicity work out. Now, any frequencies that are above half the sampling rate and any frequencies and the negative counterparts, which means frequencies below or less than minus half the sampling rate, will alias. So in practice, we'll have aliasing. We'll always have aliasing because of noise or lots of reasons. There's always something above above half the sampling rate in terms of energy content. So what we want to do then is we have a design consideration, which is to design the analog low-pass filter to control the amount of aliasing that happens. There's lots of design parameters. So we've been designing filters in the, in this case, we will design them in Lecture 5 and 6, but we have also designed them on homework 2. So ultimately, in practice, this will be an infinite impulse response filter. And we get to control things like passband frequency, stopband frequency, passband attenuation, stopband attenuation. Passband ripple, if you prefer, instead of passband attenuation. So those are our design parameters. And we're going to see later in Lecture 8, it's going to relate to how many bits that we want to represent in the quantizer. So if the quantizer is V bits, it tells us exactly what the stopband attenuation is. And I'll give you the preview now. So the stopband attenuation for the filter in dB is going to be some constant plus 6 dB per bit. So if I have 8 bits, then this is in dB. We'll derive this a little bit later. So for every bit, for every bit, I need 6 dB plus a constant of stopband attenuation. So if I need 8 bits in the quantizer, this will give me 48 dB plus some constant. If I want 16 bits for the quantizer, that means 96 dB plus a constant. This constant is usually pretty small. It's 1 to 2 dB. Some variation in this. Sometimes you'll see 4. It depends on. But for audio, it's 1 to 2, typically. We'll relate also the passband ripple to the number of bits, and we'll do that later. There's a direct relationship. Once I set the number of bits and the sampling rate, I can work backwards and find out what specification I need on the low-pass filter. So I also now know what's the stopband frequency of this low-pass filter. What's that going to be?
You're going to want to set it so that none of the frequencies that you alias are
So what is the stop band frequency? Should be half FS, or to be safe, a little less than half FS. So the stop band frequency. So this point's here. Yeah, 0.9 is fine. 0.95, something of FS. So the sampling rate, the stop band frequency is slightly less than half the, or it has to be less than half the sampling rate. Now, once I know the stop band frequency, what's the pass band frequency going to be?
Sorry.
If I know the stop band frequency, what's the pass band frequency going to be?
You need to use the 10% ratio.
10% transition, so 1.1, it's the other way. You're on the right track.
1.1 times 1.
Right. So you can say the stop band is 1.1 times the pass band, or the pass band frequency is, say, 0.9 of the stop band frequency. However way you want to work it.
That's just a rule of thumb.
Rule of thumb, right? You know that from, right, so f stop is basically 10% higher than the passband frequency. Again, this is a theory. The practice will be different. We'll talk about that in lecture 10. The theory here is discrete blocks cascaded together. One block does analog low-pass filtering, one block does sampling, one block does quantization. But again, it's analog low-pass filter. It's a continuous time. Its job is to enforce the sampling theorem as much as possible. Control the amount of aliasing. The aliasing will happen. It's just a matter of controlling it. So if it's an audio codec, we don't want to hear the aliasing. If it's an image codec, we don't want to see the aliasing. The aliasing will happen. We don't want to hear it or see it.
What does aliasing look like?
You get jagged lines. You don't get smooth lines. Now, once we have a sampled signal that's sampled in both amplitude and in time, so we have a digital discrete time signal, we want to be able to go back to continuous time analog, play back the audio, display the video. So the next step here is digital analog conversion, and here we have a bunch of discrete samples. This is now digital and discrete time. So I have a bunch of samples, and what I want to do is ultimately convert it into a continuous time analog waveform. So how about a nice alternating 1, -1, 1, -1, something like that. We'd love to have this, in the end, look something like a sinusoid, if we could. If all things were right with everything were ideal and perfect, we'd have a really nice looking cosine that comes out, right? This we love to have come out. In practice, we'll have noise, and we have all kinds of things. So in practice, we have some work to do. We've got to be able to figure out, this is a discrete time in the time domain, and we also have quantization in the amplitude. We want to convert discrete time to continuous time, and then we want to also convert these samples taken at discrete points in time and somehow connect the dots, right, to get a smoother waveform. And we'll talk about today lots of ways we can connect the dots. We can draw lines, we can fit it with a curve, we can filter it, lots of things we can do. Talk about those today as we go a little bit. So again, the one thing we could do, just what we did as kids, and sometimes, I enjoy it, I suppose, as adults. I have a 7-year-old, and I do. So this is something she did, I guess, more when she was 5. So you just connect the dots, and you get this jaggedy line, and we'll see that today in demo. In passive, this would be our conversion step, right, to connect the dots. So we'd like to come out of that. So out of the conversion step, we'd love to have these lines.
So we'd love to have those lines?
Yeah, we'd love to have those lines, because what we can do is because that's a way to convert from discrete time to continuous. So the first thing we need to do is figure out, what does that point look like in continuous time? So what is the mapping there to continuous time? What's the first sample? When you sample, If you go back to sampling a continuous time waveform, the first sample that you might have taken is at what location in time? Yeah, capital T, that's the sampling time, that's it. So if I were to do sampling, I'd be taking samples of this analog continuous time waveform at integer multiples of the sampling time. So now if I want to go the other way, I start with discrete time and go to continuous time, I have to connect discrete time to continuous time. So that first sample here is equal to the sampling time. So I have a notion of a sampling time because I'm going to use that to reconstruct from this discrete time digital representation to a continuous time analog representation. So now once I know that the distance between adjacent samples in my discrete time signal is the sampling time in seconds, that helps me convert the discrete time axis to the continuous time axis. The next thing is I have now these digital amplitudes. I'd like to get back to something that's ultimately analog. So if I connect the red dots that I have here and come up with what looks like a sawtooth waveform, now that's not a sine wave. Let's say that I started with a sine wave. So the next step I do is I apply an analog low-pass filter, and its job is to clean up artificially introduced frequencies in this discrete to continuous conversion step. Go ahead.
Is the sawtooth, is that going to be generated by, like, for instance, the software is interpolating between?
Only because of the data I have. So this has to do with the data I have and the type of conversion. So in this
and the way I imagine it, like if you have a digital system and you just sample it raw, you're going to end up getting a square wave because it's going to be stay at the high value, and then once you sample one,
it depends on the signal you're sampling. If you're sampling a sine wave and you only have two levels of representation, then you'd go from 1 to -1, 1 to -1, and you'd have a square wave. But if you have more bits than that, than just one bit, then you get all kinds of levels in between.
So you're interpolating.
Here we're interpolating. So this discrete to continuous conversion process does two things. One is to figure out how to convert discrete time to continuous time. Second, I need to connect the dots, the sample values I have in discrete time, so I can find out what is the value of the signal in between the samples that I have. I could also have done, as you suggested, I could hold this sample in place and get a square wave. That's also that's just sample and hold. It's a very valid way to do discrete to continuous conversion. This is a way discrete time to continuous time conversion. So then I apply an analog low-pass filter, and its job is to get rid of frequencies that would not have been captured in the sampling process. So where do you think its stop-band frequency is? It's a low-pass filter, and where do you think the stop-band frequency is?
Same
As before. So we get to reuse the same answers on the slide. So this is the same filter as before because I started with a sampled signal. I'm interpreting the distance between samples as a sampling time. So I now have associated a sampling rate, fs, with this discrete time signal. Any frequencies in the reconstructed waveform above half the sampling rate are artificial. They weren't here at this point in the system before I go through the discrete to continuous conversion step. So this analog low-pass filter at the output cleans up the artifacts that are introduced by the discrete time to continuous time conversion step. And so so if I'm a little bit sloppy in the discrete to continuous conversion block, I have to have a better analog low-pass filter. There's a trade-off. So whatever work I don't do in the discrete to continuous time block, I have to do in the analog filter block. So if I go with sample and hold in the discrete to continuous time conversion block, I have to have a more aggressive low-pass filter. If I use linear interpolation, a little less aggressive low-pass filter. And there are other things I can do in the discrete to continuous step. I can do sync interpolation, lots of things I can do. All right. So let's talk about sampling, a little more about sampling today, and then we'll fill in these other steps in subsequent lectures. All right, review. So way back to signals and systems. In so sampling in the time domain, many signals originate in continuous time. Talking on the cell phone, for example, playing acoustic music. So if you're talking on the cell phone, the pressure waves impinge on a transducer. The transducer creates a voltage and current signal in continuous time analog. We then sample it, send it through an ADD converter, and we now have a stream of digital discrete time data, which we can compress the transmission. If we sample a continuous time signal at isolated, equally spaced points in time, we obtain a sequence of numbers. So we can look at the sampling process in two ways. One is to return a discrete time signal of sampled of just the amplitude values of the signal taken at these integer multiples of the sampling time. So just visually here, so if I have my f of t signal here, and this is purple, we're going with purple here. Blue, what's your guess there? Blue, we're going with blue. All right, we'll switch to blue. All right, so the f of t here is being sampled at equally spaced points in time. So a little n of 0 corresponds to the origin. This is little n of 1. And I just keep taking amplitude values at integer multiples of the sampling time. So I'm left with, so one way to look at what I've done is I simply have a discrete time signal, little f of n, and I simply have the amplitude values and nothing more. This is the more common case for us in lab. This is the way we get signals on and off the board that we're using. All right, so we'll put in some test signal if we want to onto the board, and we send it through the ADD conversion process. Part of that is to sample the signal in continuous time to give us a discrete time output. Another way we can look at this goes back to homework 0 problem 1, which is to look at this sampling process in the continuous time domain. In the continuous time domain, we can model sampling as multiplying the signal in the time domain we want to sample f of t with this impulse train, and the impulse train is separated by, or the impulses in the impulse train are separated by the sampling time. Homework 0 problem 1, the most important problem assigned in the class. We'll use it throughout the second half of the semester as well. So I have so this is one way to, again, what I've done graphically is showing each direct delta here, each impulse in the impulse train, having its area scaled by the amplitude of f of t at that point. And so this f of t out front is scaling the area of the direct delta at that location, at the appropriate location of the sample being taken. Now I'm multiplying in the time domain, so kind of know what's coming next. We can involve in the Fourier domain. What's coming next? That was problem 1 of homework 0. Okay, so now here's the frequency domain interpretation of sampling. Again, review. So sampling will replicate the spectrum of a continuous time signal, and the replicas occur at integer multiples of the sampling frequency. And so let's see how that plays out in the frequency domain. So we'll do two things. First step is to take the Fourier series of the impulse train. And the reason this is interesting, because the impulse train is periodic, and it's periodic in the time domain with periodicity equal to the sampling time. Right? So this impulse train in the time domain is just a bunch of direct deltas located at integer multiples of the sampling time. So and the amplitudes are 1 under each.
Where does that originate from?
This is the impulse train. This is the modeling of sampling. This is the model of taking an instantaneous snapshot when you sample something. This is an idealism. In practice, we can't take instantaneous snapshots. We take we observe a signal over a very small period of
So
time.
the idea is that it's just showing how when you sample, like for instance at you're sampling these 0 hertz, what you're actually sampling is 0 hertz and every single multiple TS.
Well, it's not 0 hertz. It's the impulse train is still in the time domain. It's still in the time domain. So what it means is that this impulse, for example, at the origin is saying that my impulse gets scaled by the amplitude value of f of t at the origin. I'm plucking off that value.
I guess what I meant was like when you're sampling at some sampling rate, TOS, where you're actually sampling, what the frequency you're actually sampling is every single multiple.
It's when you sample, so the effect in the Fourier domain is we get a convolution effect. Right, so again, this is the time domain for the impulse train. The Fourier transform of this is another impulse train. And the impulses are, so it looks like if we were multiplying in the Fourier domain, your observation would be right. We would only pick off 0 fs, 2 fs. But we're not multiplying in the Fourier domain, we're convolving in the Fourier domain. Right. And then we have a scaling in the, this is scaled by the sampling rate. The area is scaled by the 1 over TS. Or FS to be easier to write here. So it's an impulse train in the Fourier domain, and the impact will be that we're going to convolve in the Fourier domain. All right. So the two things we're going to do, one is to first get a Fourier series expansion of the impulse train in the time domain, and then look at the product in the time domain of the sampled signal in the impulse train. Then we'll go to the Fourier domain and see what happens. All right, so this, it's one of these things to look up or compute, but the Fourier series of an impulse train has, you can look at it as another, so there's one way to go, of course, is that another way to derive this relationship is to do it through convolution in the Fourier domain, which you can do. This is another way to go about it, which is do the Fourier series first and then the Fourier transform. So the Fourier series expansion of the impulse train gives us a sum of harmonically related cosines. This is a Fourier series. So I have a cosine term at the fundamental frequency in radians per second. I have the second term, which is twice that fundamental frequency, and so forth. The coefficients are the same for each of these sinusoids, at omega s to omega s, and so forth. And I have a constant term of 1. All right, so in the Fourier series, this constant term of 1 is the area in one period. And the period here, it can go from half the sample time to minus half the sample time. That's one way to, or go from 0 to TS, but don't include TS. So the fundamental period, visible back row? All right, so if we continue on, then there's a Fourier. So this is exact expansion. It's not approximate because we're going to keep an infinite number of terms in the Fourier series. If we go ahead and multiply through the signal we want to sample f of t in the impulse train, we get this. So we get a scaling of 1 over the sampling time times these terms. We get f of t comes through unchanged, other than being scaled by 1 over ts. We then get an amplitude modulated version from this term, from the second term here. in the Fourier Series expansion. So we get 2 times f of t times cosine omega st, and so forth. So we get a bunch of amplitude modulations happening at multiples of the fundamental frequency. So if we look at what happens in terms of the frequency domain, if I start with a baseband signal, ideal baseband signal, no noise. So the max frequency is f max in hertz, 2 pi f max in radians per second. If I sample this, it means that the actual spectrum comes through as is, which is that part. And although it's scaled by 1 over ts, but the shape doesn't change. And then I get replicas at, so I shift this spectrum f of omega by omega s. I shift it to the right by omega s, shift it to the left by omega s. Or in this case, if it's, so we're in radians per second. So we shift left by omega s, and we shift right by omega s. So here's the first term, gives us these, those parts of the spectrum. The next term shifts the spectrum of f of t, left by 2 omega s, and right by 2 omega s. So that gives us those 2 terms. And so forth. Just keeps replicating, left and right. And then, okay, this is great. So now I've sampled something, and now the question is, how do I recover what I started with, f of t, with what I have, which is g of t? So what do I do?
Filter.
What kind of filter? Yeah, usually in this class, half the answers are filtering of some kind or another, so you're good. Low-pass filter is good. And where would your passband frequency be?
From 0 to
0 to
W max.
W max, right. So 2 pi f max. Where'd the stop band frequency be?
Pretty much everything above.
Well, you love that. Yeah, we can't have a. I mean, great to have an ideal. So you could do an ideal filter. I mean, I've given you an ideal spectrum. You could do an ideal filter, I suppose. But a more realistic filter, I'd have to have some roll off, right? 10% roll off
What sense?
from passband to stop band,
Oh.
right? So I'd have a filter that really would look more like. So the ideal filter would just do this. That's your ideal case. The more realistic case is that I have some roll off from passband to stop band, right? Go ahead.
So I think this is an odd question. But so we're shifting to the right and left by omega s and 2 omega s. Could the first term not be viewed as f of t times? Oh, never mind. I answered my question.
Okay. Excellent. Excellent. And you can kind of see that. Okay, so let's keep going. So I'm going to apply a low-pass filter to recover the original signal from the samples, the sampled signal. And a low-pass filter is the ideal way to do it, provided that I have a gap to work with. All right, so I want to have a gap here to work with. Now, a gap is going to occur if the right edge of the baseband spectrum is less than the left edge of the first replica. Right, so this right edge of the baseband spectrum is 2 pi f max. The left edge of the first replica is 2 pi fs, which gets us right here in the middle, minus this distance. So the left edge of the first replica is 2 pi fs minus 2 pi f max. That puts us over here in the first replica. And the right edge is simply 2 pi f max. So as long as the right edge of the baseband spectral component is less than the left edge of the first replica, we have room there for the low-pass filter. And if you look, just a very simple algebraic step here, by bringing the 2 pi f max over to the left and dividing through by 2 pi, and you get the very familiar sampling theorem result that the sampling rate has to be greater than 2 f max. Go ahead.
If the frequency band from 2
still be able to filter it if you would just cut into your.
You'd have aliasing, right? So if you don't have enough room between replicas to have a filter roll off, it means you're just going to get beat. And in fact, in practice, the stop band isn't 0. So in practice, yes, we're always going to get some piece of this first replica when we low-pass filter. It's just so we have to design a low-pass filter in practice to reduce that leakage.
No, what I meant was what I meant was, for instance, like let's say our pass banding goes like we want 0 to 10 kilohertz.
Mhm.
Would we be okay if maybe we were like we tried sampling like for instance only up to like 9.5 kilohertz and we allowed that like extra half kilohertz to let it roll off?
Yeah, so what we do is, so that's exactly what we might do in practice. So if I know that I want to capture from 0 to 10 hertz, let's say I sample at 20 hertz. It means I can capture up to 10 hertz.
Yes.
But now I have to figure out what kind of anti-aliasing low-pass filter I need. I might put the pass band at 9 hertz and the stop band at 9.9. So I'll lose a little bit of my signal that I want. I'll shave off a hertz of my signal, but at least I don't get aliasing much. I reduce the amount of aliasing. Yes, we do that. All right, still more review. Sampling theorem, which is just a result of, byproduct of the previous slide. So in the sampling theorem, if we have a continuous time signal x of t with frequencies no higher than f max, we can reconstruct from its samples if the samples are taken at a rate fs greater than 2f max. So some keywords in here. Let's see. Continuous time signal with frequencies no higher than f max can be reconstructed from its samples if the samples are taken at a rate fs greater than 2f max. Lots of idealisms in this statement, and it's a great starting point. It's a great starting point. And a few terms here: Nyquist rate, which is 2 times f max, and Nyquist frequency, which is half the sampling rate. First question up, what happens if fs is equal to 2f max, which we sometimes do in practice? What happens?
If you have an ideal filter, it should be okay.
Ideal filter's okay. Ideal filters are usually okay. Hard to build? Sure. But let me narrow that question down. In the time domain, what happens if fs equals 2f max? I have no gap in the frequency domain, but that's true. And what happens in the time domain?
Oh, it's a constant, right?
I get a constant if the input signal is?
Wait.
You're on the right track.
You're sampling right?
F max.
But what I just did it. What sinusoid do I need?
Cosine?
What's the time signature?
Okay.
Cosine is actually okay, amazingly. All right, so let's do the cosine. So if we sample the cosine, right, if you sample cosine, if I have fs equal to 2f max, oops, try again. Now what happens if fs equals 2f naught?
It's going to be 1.
You're half correct.
It's going to be 1 negative 1.
Very good. Full credit. Okay. Close. So what happens here? If fs is 2f max, this gives us cosine 2 pi n, which is minus 1 to the n, right. So that one gets through amazingly. That one gets through. It's the fastest alternation, right? 1 minus 1, 1 minus 1. It's the highest frequency possible. in a discrete time signal, or a sampled discrete time signal. All right, now, what about the sine? What happens for sine? I get all zeros. All right, so I do this for the sine. I sample. I get sine pi n for this case. If fs equals 2f max, or 2f naught. I get sine pi n, 0. Doesn't make it through. So this is the one corner case, and that's why we exclude, that's why it's a greater than and not greater than or equal to, because there's this one signal that just doesn't get through. If you're willing to, bet, or if you're willing to let that one not get through, and all the other possible sinusoids get through, then we'll do greater than or equal to, or less than or equal to. Depends on how you want to write it. So sometimes we do, sometimes we simply use fs greater than or equal to 2f max. Sometimes. All right, we've done this for audio signals already. For hearing, for normal human hearing is 20 hertz to 20 kilohertz. There are people that do hear outside this range. It's just an aggregation over a lot of testing. A lot of people under test. So this is our normal human hearing. So what do we do in terms of, we want to sample an audio signal. We want to apply a low-pass filter before sampling. We want to pass frequencies up to and including 20 kilohertz. And then reject high frequencies. But we know from filter design in homework, certainly in homework 2 and homework 3 as well, that we need this roll-off between passband and stopband. So if the passband frequency is 20 kilohertz, our stopband frequency really is going to be 22 kilohertz.
Is that why CDs sample at 44 kilohertz?
Right, so 44 point, yeah, so good reason why CDs have to sample at greater than 44 kilohertz. And 44.1 is
As
the...
opposed to sampling just at 40?
Right, 40 wouldn't cut it because we'd have, again, it's back to your earlier question, if we sampled at 40 kilohertz, I'd have to shave off the high 2 kilohertz here to make that work. I'd have to have my passband frequency at 18 kilohertz and my stopband at, say, 19.9 kilohertz. I'd rather capture the whole audible spectrum, so I'll put my passband frequency at 20 kilohertz, my stopband frequency at 22 kilohertz, my sampling rate at greater than 44, greater than 2 max, twice the stopband. So 44.1 kilohertz satisfies that. Now, why 44.1? It turns out that, we talked about this already, but what you could record in 1982 at that rate was pretty limited. So if you use a TV format called PAL or CCAM and you stored 3 audio samples per row of video in each frame, you get a 44.1 kilohertz sampling rate. The other side is how big is the CD, and that comes from, I think the Sony, I've heard someone mention this already, the Sony CEO wanted a certain piece of classical music to fit on one CD, which is 75 minutes long. It depends how you play it, but that's the capacity of an audio CD, given the sampling rate of 44.1 kilohertz. Right. Sampling theorem. There's some wonderful things in the sampling theorem, a lot of idealisms in the sampling theorem. So let's kind of go through those one at a time and discuss how we might do that in practice or deal with meeting the assumption in practice. And these are good, you've dealt with these on multiple choice questions or, disprove the claim or whatever. So continuous time signals are for assumption number 1, continuous time signal has absolutely no frequency content above f max. So love the absolute statements. Easy to blow holes through. So what's in practice? Why is that not met?
Yeah.
Thermal noise at pretty much all frequencies out to 10 to the 15th or something hertz. We're going to have at least background noise. So we're going to have content above any F max that we would possibly be interested in for sampling a signal. How do we deal with it? So we got noise. So not met because of noise. And then how do we deal with it? Yeah, a filter. What a good. So not met at least due to thermal noise, and then we can control, again, we can't filter out all frequencies above F max, but we certainly can control the amount of filtering. That's our stop band attenuation. It's a type of filter design we choose. So in practice, we design a filter, design the anti-aliasing filter. So we design a low-pass filter to reduce content above F max. Next one. Sampling time is exactly the same between any two samples. Metaphysical perfection between sampling times. Go ahead.
Would the main reason for that not being true be that, like in software, you're going to have, your instructions are going to take different amounts of time to process, and the timers are never going to be accurate. So the time between the sample being processed will be different each time.
So you have insight from just profiling the runtimes of software. There's always some error or jitter in the clocks. That's exactly right. So clocks are not perfect. They have a little bit of miss from one zero crossing to the next. The good news is that we can control this down to almost 1 part per million, certainly 10 parts per million with the right circuit design. So that's a relative error of 10 to the minus 5 or 10 to the minus 6. Just amazingly accurate. It's a matter of how much money you want to spend on that, but we can get, so we can't get exactly the same, but we can get pretty close relative to the sampling time. Missing 10 parts per million is not much. In many cases, good enough. Okay, so circuit design we can control. We can control this with circuit design. Sequence of numbers obtained by sampling is represented in exact precision. No. So first, there's no quantization in the statement of the sampling theorem, but it does assume, so if there is quantization, it complicates this. There's no quantization here, but just the fact that you observe an analog amplitude, that you're trying to measure an analog amplitude. Whenever you measure a system, there's always some distortion, Heisenberg uncertainty, nothing else. There's always some uncertainty in the measurement. And so it's not exact precision. There's always some error in the analog amplitude measurement.
So would you be technically wrong if you said that precision and floating point you're setting round numbers since it's not talking about quantization?
Well, here we're not, all this is analog amplitude, right? And we're not in any way quantizing the amplitude. But just trying to measure the analog amplitude of the waveform we want to sample, we won't be exactly, there'll be some error in there. Now, if we later talk about quantization, floating point numbers can't represent all possible numbers. In fact, it's non-uniformly spaced on the real line what you can represent. That's a related issue because we like to be, once we quantize, we can control the amount of distortion by how many bits we can capture off the analog amplitude. And then how do we represent that in a format, floating point or something? So that's a later consideration, but definitely one that we want to do when it comes to the full data converter. That includes quantization. So this is all the A to D side. Right, this is all sort of the sampling side. The last piece is the conversion of the sequence to continuous time is ideal. The sampling theorem says it's possible, if you sample at more than 2f max, to reconstruct the original signal. It doesn't tell you how to do it. It just says it's possible. There's some ideal conversion, which is through an ideal low-pass filter is how you would do it. We can't build that, so now we're going to have to figure out how to approximate this ideal low-pass filter.
Why don't you still have to interpolate and sample?
Yeah, so if we, it depends, absolutely, so it depends on how you are viewing sampling. So if you're viewing sampling as happening only in continuous time, so I start in continuous time with f of t, and after I sample, I stay in continuous time. To go back to f of t, as long as I don't have aliasing, I low-pass filter with an ideal low-pass filter, and I can go back. And so that was this slide. All right, so as long as I can put in my ideal low-pass filter, I can get back to the baseband. Right. Now, if I look in discrete time, now this is just a sampling. This is not the full data converter. But this is just one piece of the data converter. This is just the sampling part. If we include the rest of it, now we have to worry about exactly what you've asked about. So now if we have to go back a little bit. Now if we look at the full story, remember here sampling is just playing a role in analog to digital conversion. We also have the anti-aliasing filter, quantizer in the A to D converter, and then in the D to A, which is the reconstruction part of the sampling theorem. It does still give us some guidance on how to go from discrete time signal, digital, to analog continuous time signal. I have these two steps to do, and I still have to convert from discrete time to continuous time through interpolation. Now, it turns out there is some insight on what that interpolation should be, because we know that really what we really want is to go from discrete time to continuous time, and then once we're in continuous time, we apply the low-pass filter to pick off the baseband. But this step here can take many different flavors. It can be zero-order hold, could be linear interpolation, could be itself a low-pass filter. In fact, they are. Zero-order hold and linear interpolation are kinds of low-pass filters. We'll see that in Lecture 7 slides. Quickly do a demo here of sampling in action with the sinusoid. This is from DSP first, the column shape for Yoder. So we'll start with cosine at 600 hertz. We'll just do the one signal. And there's a phase shift to pi over 3. Doesn't matter much here. So it's 600 hertz, or 1200 pi radians per second. It's a sine wave. Sinusoid, it's a cosine, whatever. Cosine with a phase shift to pi over 3. We know that if we're going to sample this, we want to sample, it's a finite observation case. So we know we need to sample, we know that the max frequency is more than just 600 hertz. There's some bandwidth because of finite observation. It could be 10 hertz, who knows what it is. It's something small. So we really want to sample at more than twice F max. F max here is probably 610. So we're going to sample at more than that, more than 1220. So we're going to sample at 1250. And if we sample this, we still pick up, if you look at, so here's the cosine. And here, there's a sample missing at 0. Don't know why. There's one at 0, one here, one here, one here. So I get slightly more than 2 samples per period of the cosine. And I'm following at least the alternation of sine well enough. Okay, so now let's go ahead and do the zero-order hold, which is just connected, basically hold the value plus or minus half the, this is a non-causal view, but hold the sample for half or plus or minus half the sampling time, and then we get the staircase approximation in reconstruction. Doesn't look much like the cosine. The good news is it does capture the right frequency of zero crossings. Right, so the distance from one zero crossing to another is half the period. So at least that's being captured correctly, but not where it occurs. But how often it occurs is correctly captured. Okay, so that's not Great looking. Now let's do linear interpolation, which is to take the samples that we have and just draw straight lines to connect them. And a little better interpolation. Zero crossings are done at the right frequency, but not the right location. Last, we do an ideal low-pass filter by filtering this discrete time signal with a truncated sync in the time domain. So sync would be the time domain response for an ideal low-pass filter, but it's two-sided sync. Can't build that. So we truncate it and use it as a filter, and we get much better results. Still not as good as it could be. Looks better than the other two cases, but I'm still not capturing the times of the zero crossings, but I am capturing how often they occur. Let me do oversampling. So instead of sampling at just more than 2f max, let's sample it more than 8f max. Remember, in a system, ultimately we have to pick a sampling rate. And higher the sampling, the better we track the time domain waveform, but the more complexity we incur. So here is at sampling at 4850 hertz, more than 8f max. I get slightly more than 8 samples per period of the cosine. Reconstruct with a square wave, zero order hold, I get a staircase approximation. It's better looking with 4 times oversampling. Linear interpolation, pretty close. Pretty close. I miss here on the valleys and the peaks in terms of the actual height they obtain or the depth they obtain, but I got my zero crossings in the right locations. Last is the sync interpolation. Really, really good. Except, where's it missing? Early. What do you think that has to do with?
There's no sample.
There's no sample in the very beginning, so this and remember I'm applying a filter that has a truncated sync impulse response, so what's happening here? Group delay, very good. That's the group delay in the filter. It takes a while to fully respond. Okay, thank you, and see you on Friday, and I have office hours next hour and 45 minutes.